Modern physics is built on a specific set of primitives: mass, energy, and spacetime. We treat these as the irreducible bedrock of the universe, the starting point for every equation in our standard models. But when these primitives are pushed to their mathematical extremes, from the centers of black holes to the earliest moments of the universe, the equations diverge. The model breaks, revealing that our fundamental assumptions cannot account for the behavior of reality at its limits. We see the evidence of this failure in gravitational singularities that defy description, in the blow-ups encountered when modeling fluid dynamics at high velocities, and in the persistent need for dark matter to explain why galaxies don't fly apart. For engineers and researchers, moving past these roadblocks requires a reconstruction of physics from its first principle: information. This is the framework of new subquantum informational mechanics, or NMSI. NMSI suggests that our current models are not absolute truths, but mathematical patches. By shifting the focus to the informational substrate, we can address the gaps that standard primitives simply cannot bridge. NMSI operates on an ontological inversion. It assumes that what we perceive as the physical world is the secondary result of a much deeper process. In this model, information is the primary substance. It is the substrate that computes physical reality, rather than a secondary property arising from the movement of matter or energy. This forces a new definition of the vacuum. It is no longer an empty stage, but a high-density logical medium. This medium consists of infobits, discrete, inactive units of oscillatory information. They form a logical memory field that exists in a state of potential across the entire universe. Mass, charge, and spacetime emerge only when these infobits undergo coherent phase transitions. Physicality is the observable output of these subquantum informational dynamics. Framing the universe as a computation running on a discrete substrate provides a specific advantage. It means the laws of physics are harmonic scores that can be mapped and engineered. To interact with this substrate, we need its specific mathematical architecture. This is the Riemann oscillator network, or RON. RON is a finite computational network with approximately 1 trillion nodes. Each of these nodes corresponds directly to a non-trivial zero of the Riemann zeta function, creating a defined structure for the subquantum vacuum. Every node in this network acts as a fundamental oscillatory mode. Because these nodes are defined by the zeros of the zeta function, they possess specific, non-random angular frequencies. These frequencies dictate the rate of information transfer throughout the vacuum. Energy is essentially a measure of this data transfer rate across the different modes of the network. This structure replaces the probabilistic uncertainty of standard quantum mechanics with a rigid, number-theoretic reality. The vacuum functions as a precisely tuned resonance chamber. Within this network, only the specific harmonics permitted by the math of the Riemann zeros can exist and interact. Addressing these nodes requires a mechanism called pi indexing, where blocks of digits from pi provide deterministic coordinates within the network. As these addresses are mapped into the network, we encounter a hard threshold at a block length of 24. This is the scale where the finite network transitions from discrete behavior into a correlated continuum. Below this length of 24, the addresses are sparse. Collisions between data blocks are rare, and the resulting mapping appears statistically random. But as the block length reaches 24, the finite capacity of the network forces a structural shift. At this threshold, the system is forced into phase-locked loops and repeating patterns. These correlations are the mathematical origin of the macroscopic physical features we see in the cosmos. This threshold of 24 is a derived necessity. It is a product of the internal consistency required for the network to address its own nodes without conflict. Because this transition occurs at a specific mathematical scale, the resulting synchronized modes project onto the spherical harmonic basis of the cosmic microwave background. This projection naturally generates the low-level coherence and large-scale patterns that traditional models struggle to explain. This creates a point of no return for the theory. By establishing a fixed, calculable boundary at L equals 24, NMSI provides a clear criterion for its own refutation through experimental data. Within this synchronized network, localized decision nodes begin to form. These are central logical oscillators, or CLOs. Unlike a probabilistic wave function, a CLO operates through deterministic phase coupling. The behavior of a system is determined by resonance and logical synchronization rather than chance. In this framework, a collapse of a wave function is reinterpreted as a loss of local coherence, a specific breakdown in the phase structure of the logical network. This oscillatory structure also changes how we view mathematical singularities. If reality is a network of resonating nodes, a physical infinity cannot actually form. Instead of a singularity, NMSI identifies a dynamic zero. A dynamic zero is a transient node where energy phase cancels in one vector but is coherently transferred to another. As seen in this simulation, what looks like a catastrophic failure point is actually a stable redistribution of energy into a twin vortex system. This redistribution prevents the numerical divergence that typically crashes fluid solvers. In hypersonic modeling, reclassifying singular blowups as dynamic zeros allows researchers to stabilize simulations and accurately predict heat flux and skin friction where standard equations fail. Replacing the singularity with a resonating node reveals a universe that is a flawlessly self-regulating informational processor, capable of maintaining regularity even at its most turbulent scales. When gravity and mass are understood as emergent effects of oscillatory interference, we can move from observation to replication. We can engineer these effects artificially. This engineering lead is the foundation of twin quantum computing, or TQC. A TQC core uses mirrored entangled oscillatory centers. It computes through continuous phase harmonics within a stable cavity, rather than relying on the binary logic of traditional gates. This architecture mirrors the natural twin vortex logic found in planetary feedback structures. By aligning with these natural harmonics, the system can scale its logic from the subquantum up to the macroscopic level of an atmospheric cyclone. The goal of TQC is to develop logical systems capable of resonating with these massive planetary oscillators, effectively decoding the data flows present in the Earth's natural systems. TQC enables logical systems to directly speak the universe's native informational language, shifting our relationship with computation from instruction to resonance. The transition to NMSI marks an evolution in how we approach the physical world. We are no longer just passive observers of particles. We are now identifying the specific subquantum harmonics that govern their existence. The mathematical framework, from the L24 threshold to the mechanics of the central logical oscillator, provides a concrete path for further research and invention. We are moving from discovering the rules of physics to participating in the informational logic that generates them. If you enjoyed this video, please give a like and subscribe. And what would be really helpful would be some suggestions for future videos. Today's video was brought to you by Synestec Systems LLC, founded by Shane Persinger.